Correlations are all around us in everyday life. People who are taller tend to weigh more than people who are shorter, so height and weight are correlated. The amount of ice cream sold increases as the outdoor temperature goes up, so those values are also correlated. Entanglement, on the other hand, is a special kind of correlation that exists between quantum particles. But this kind of correlation is much richer than that between height and weight or ice cream and temperature. For example, two photons can be set up so that a certain property called polarization is correlated in the following sense. Initially, each photon has a certain probability of being found with a particular polarization. But once we measure one of those photons and learn its polarization, we automatically know with 100% certainty the polarization of the other. But how is that possible? And why is this the case? Well, that's the very nature of entanglement. And this is why we don't just call it correlation instead of entanglement. It turns out that the nature of quantum correlations is much different than the classical correlations we're used to experiencing. So it's helpful to have a different term to describe it. And the theory itself can get pretty technical and involved. But at this point, you might already be wondering, does anyone care? And is this useful for anything? The answers are yes and yes. Entanglement is of great interest at both the scientific and philosophical levels, and due to its striking properties, has been the source of many discussions on the nature of reality. But on a more practical level, entanglement is also finding use in a number of areas, including in communication and security. For example, one popular paradigm for using entanglement in communication is when you want to take information at one location and construct or recreate that same information at another location. There are a lot of details involved, but this basic idea is at the heart of a popular protocol called quantum teleportation. Security is another common application of entanglement. In this paradigm, entanglement can be used to detect when something has been altered that shouldn't have been. For example, imagine you are a cybersecurity expert running a protocol or algorithm to protect sensitive data. Some algorithms are based on quantum physics by using pairs of particles that ought to be correlated with one another, like two photons sharing the same polarization mentioned earlier. But if you suddenly notice that your photons are no longer correlated as they should be, then that gives you a clue that something has broken down. Or even worse, that an unwelcome visitor has infiltrated your security setup. Loosely speaking, this concept is at the heart of some protocols within an area of quantum cryptography known as quantum key distribution. Security and communication are just two ways in which entanglement, a particular correlation at the quantum level, is finding applications today. In an exciting turn of events, there is still much to learn about this quantum phenomenon, both in how it may be useful in applications and the clues it may provide into how nature operates at the small scale.